right, so we can just continue with problem solving. Any question? I know that the topic might be like, looks complicated, but as you practice, you'll understand the concept and try to apply it on circuits, okay? So,
Homework is due next Monday, right?
yes, I intended to have it before the midterm so that you can practice using the so this is the main idea. So with the feedback, you reduce the gain, which is the main disadvantage. But on the other side, you improve other parameters like the input impedance and the output impedance, depending on the topology or the configuration. Okay. How to do the feedback analysis? Okay. So the goal of feedback analysis is to determine, as the AC analysis. When we do the AC analysis, we determine the gain, the input impedance, and the output impedance. These are the main three aspects for the AC analysis. So with feedback, we need to find the gain with the feedback. We give it the subscript F. So it could be A, V, F, A, I, F, A, R, GF, or A, Z, okay? Depending on the type of the amplifier. Also, the input impedance are in F, and the output impedance or resistance are O, F. There are three main methods. Direct method, and we did that many times in the previous circuits, and this is a very complicated method, especially when you take into consideration, the loading effect of both, because beta, the feedback network, loads the output of the amplifier, and the amplifier loads beta. So they keep loading each other because they are in a circuit, right? So if you take the loading effect of both systems, this is going to make this method horrible. It's very difficult to apply. The easiest way to apply this method if you have an ideal no loading. Okay, so it's something like this. You see, this is an ideal amplifier, right? This is not an ideal amplifier because this one has Ri and Ro. This one, Ri is infinity and Ro is 0. So this is an ideal case. This case you can apply the direct method. But if you assume you have a resistance here and a resistance here, then things are going to be very complicated to analyze using this direct method. Okay. The next method, which is much easier, is called the loop gain analysis method. Remember when we did the loop gain, how to find the loop gain? We cut somewhere, we apply this voltage, and measure the received end voltage, and we divide with a negative sign. This is the loop gain. So you need to find the loop gain, the A times beta, okay, or A times B. And again, don't confuse beta here with beta of the transistor. Okay. This is not the current gain of the transistor. This is the feedback network. The third one, this one has shortcoming, as we're going to see. This one is what we're going to use, okay? The systematic approach. So if there's anything that you can take home out of this lecture, the whole topic is this method here, okay? And expect to have a question in the midterm using this method, okay? So the systematic approach. Again, if you have ideal case, meaning that the feedback network does not load the amplifier, you can use this one. But if you have a non-ideal case, which is the practical case, that means that the feedback network loads the basic amplifier. Okay, let me just do something quickly. Okay, now we start with the direct method. All the methods you need to identify before you start analyzing the circuit, you need to know what topology you are working with. Is it voltage, 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 current, current, voltage, or current, current? Okay? So what's that feedback signal and what's that sample signal? Is it current or voltage? Next, you need to replace active devices, any transistor, bipolar or MOSFET transistor, any operational amplifier with a proper model, T model, hybrid bi model, and so on. Then draw the complete circuit with that model. Okay, so like this one. Okay, so here we replace the amplifier or whatever with the model, this one with the model, and then you analyze the circuit. Then, with the circuit, everything exists. Don't remove anything, don't delete anything. Find the feedback gain, the feedback input resistance, and the feedback output resistance using general circuit analysis technique. Use KVL, KCL, loop methods, mesh current methods, and so on. Feedback analysis using this method, as I said, is difficult compared to the others unless you assume ideal circuits. You know, the beta or the feedback network is not loading the actual output. And this is not the case because practical cases we do have loading, right? The next method is the loop gain analysis method. Again, the first step is the same. You need to identify the topology. Is it shunt, series, shunt, and so on. Then you need to take off the feedback network by itself. You need to take it off and find the parameter beta. Okay, remember beta works opposite of the amplifier. The amplifier works in certain direction, right? So the amplifier itself works this way, beta works this way. So this is the input of the amplifier, this is the output. This is the input of beta and this is the output. Okay, so it works this way. So you have to take this beta out and do proper connection here based on the quantity. If you are measuring, if you are sensing here, if this is sensing or mixing current, then you have to have a short circuit here. And here on this side you apply a source. And then you measure the output feedback quantity divided by the input quantity. Okay? So you need to isolate the feedback network beta, and this is important for two things. First, it gives you the ideal negative feedback gain. The negative feedback gain ideally is going to be 1, the reciprocal of this value. So if you find beta 0.1, meaning that the ideal amplification is going to be 10. 0.01, then the ideal amplifier gain is going to be, like the feedback gain is going to be 1 over 0.01, which is 100. Then use the method of finding the loop gain. We described this back, if you go back to slide this one, slide 9, okay? So this is how we find the loop gain. Loop gain is this times this. And how do you find it? You cut somewhere. You can cut here, anywhere. And then you have to terminate this receiving end by the same resistance seen before cutting. So if you see something here, there's a resistance, you have to terminate this with the same resistance, right? Then you find the ratio X received by X transmitted. And X could be a voltage or current, could be I or V, depending on the topology and the signal. And then you divide XR by XT with a negative sign. This gives you the loop gain. So you find beta, then you find the loop gain. Once you know the loop gain now, you can find, use the value of A times beta together with the value of beta to determine the A. If you know A times B, and you know B, then you'll be able to find A. Once you know B beta, you know A times beta, you know A, then you can find the feedback gain with this formula. A divided by 1 plus A times beta. The problem with this method is that you cannot move further. It stops here. You cannot use this for R in and R out, because there's no way to find it unless you do something further analysis. Okay, so it just gives you one of the 3 parameters, which is A sub F. It's a very good method, but you cannot use it to find the input and output resistances as you go. Now we go to the third one, which is the systematic approach. This is what I want you to understand how to implement. Again, the first step is to identify the feedback topology. Do you have a voltage, or voltage, current, voltage, and so on, or shunt, series, shunt, and so on? Then you need to separate beta again and find the value of beta, similar to the previous one. And here how to find beta, okay? And again, this figure is taken from a different textbook, so the other textbook uses K instead of beta, okay? But this is actually beta, okay? And so on. So, if you take beta, and as I said, beta works this way, right? Let's take it as beta. So it works from right to left. If this is a voltage amplifier, voltage, then you apply a voltage, and how is voltage mixed? This is the mixed quantity, right? And this is the input. How is the voltage mixed? If you'd like to mix voltage with voltage, you mix it in series or in shunt? Voltage. Series. You cannot add two voltages with different values in parallel, right? You have to connect them in series. So if this is series, then leave it open. Don't short it, okay? And you apply a voltage and you find K or beta as V2 over V1. Okay? If you sense voltage and you mix current, this is the mix. So current, how you mix current? Shunt, right? If you mix current and it's shunt, then short it. This is why when it's shunt, shorted. If it is series, we call it separate, or just leave it alone. This is the same thing. You apply current. So this one is you sense the voltage and mix current. So beta itself is what type of amplifier is this? The output is current, the input is a voltage. No, in terms of voltage amplifier, current amplifier, transconductance amplifier, and transresistance amplifier. If the output is current and the input is voltage, this is a transconductance amplifier because it's current over voltage, okay? If beta is a transconductance, what type would be the main amplifier would be? This beta that works this way is a transconductance amplifier. What would be this one? It's the opposite, right? Because if this has the input voltage and output current, then this one has an input current and output voltage, right? So this is going to be transresistance, right? So it's this case. This one is a transresistance. Why? Because the output is voltage, the input is current. So voltage over current is a transresistance. So beta in this case is a transconductance because the input is voltage and the output is current. How the current is mixed? Shunt. How the voltage is sensed? Shunt. So this is shunt. So if you'd like to separate this one, you have to separate it this way. You apply voltage and sense the current. In this case, you have to short this to read the current. And then divide this current by this voltage gives you beta. So this is beta. Okay? Same thing, if the input is current and output is current, so this is going to be current amplifier, and the main amplifier is also current amplifier because it's going to take current and send the output on a current. So you short circuit this because if it's current, you have to short it because it's shunt, right? And you apply a current source, divide this current by this current, gives you beta. Same thing for this one. If you have for beta, the input is current and the output is voltage, then voltage is mixed as series, then leave it alone. No short circuit here, you leave it open, and then you measure this voltage, and you apply a current source, and you measure this voltage, divide this voltage by this current, gives you beta. So this is how we find beta. Okay? Now, you need to cut the circuit as we do in the loop gain. But in this case, you need to remove the beta, but not to remove it completely. Okay? You have to keep its effect at the output and its effect at the input. So you have to repeat beta twice. Okay? So remember, this was just one beta, right? A and then beta, right? Now I have to take off beta and repeat it twice, one here and one here. This one is going to keep the effect of beta for the output, and this one is going to keep the effect of beta at the input. But the new amplifier, is it still a feedback amplifier? Is this still a feedback amplifier, or this is not a feedback amplifier, right? Because you cut here, right? There's no feedback, right? When you cut here, this is a new feed-forward amplifier. It doesn't have a feedback. But it does have the effect of beta at the output and the effect of beta at the input, right? Now the question, you're gonna keep beta connected here. What to do with these two terminals? Should you short them or should you leave them open? Again, it depends on the quantity that was here and the quantity that was here. Before we disconnected and separated into two circuits, this one was connected here, right? How was that connected for this amplifier? This is a voltage amplifier, right? So this terminal was here, right? And this terminal was here. So this is the sampling terminal and this is the mixing terminal. How was voltage sampled in this side? Was it sampled in series or in parallel? Shunt or series? How you sample a voltage?
Series.
How you measure a voltage? Measure. Do you measure voltage in series?
Parallel.
Parallel, shunt. So this was shunt, shorted. Okay? How you mix a voltage? How the voltage was mixed? Series. Leave it alone, leave it open. Okay? Same thing here. This is a current to voltage. What's the meaning of this? Current to voltage is trans resistance amplifier. So the main amplifier is going to be trans resistance. The feedback network is going to be transconductance. You remove the transconductance feedback network and you repeat it twice. One connected to the output, one connected to the input. What to do with the other two terminals? This was connected here. So this was mixing of current, right? How do you mix a current?
Shunt.
And shunt, shorted. This was connected here. How do you sample a voltage?
Shunt.
Shunt, so short. So we repeat beta twice. One at the input side and one at, we don't remove it completely, okay? We have to keep its effect, right? It was loading the output, and this is loading this, so you have to keep the effect at the input and the output to have the exact same circuit. But the only thing is that this is no longer feedback amplifier, it's a feed forward. Question, is this the same as this? After you remove beta and repeat it twice, and you short circuit this and open circuit this and have a new circuit. The overall amplifier, is it going to be the same as A amplifier or is it a different thing? Okay.
A should work the same.
Yeah, let me show you something. Let's assume that, I think we had this circuit before. Okay, where is beta? Beta is this circuit here, right? And where is that A? This thing here, right? If I remove completely this and I short circuit this, this is A. This is the original amplifier without any feedback. But I'm not going to do this. I'm going to keep this twice. One time here, one time here. Yeah, sorry. No. Okay. So this is R1, R2, and this is, or actually this is R2, R1, whatever. So I repeated the feedback network twice. And I cut here. So this is no longer a feedback network, right? But is the gain of this one the same as the one without these two circuits? Are they the same? No, because now this R1 and R2 are in parallel with this. If you do AC analysis, this is going to be ground, right? So now RC is in parallel with this one. Also, this voltage is not ground, right? So the gain of this amplifier, we are no longer going to call it A. We're going to call it A prime. We're going to give it a new name. It's the same A, but with the effect of feedback at the input and the output. It's not without feedback completely. It's with the effect of feedback left at the output and at the input. Okay, now this was connected here. What should we do with it? Like, should we do this? Should we leave it like this, or should we short it to the ground? What do you think? This was a sensing element, right? It was sensing the voltage. How you sense the voltage? How you measure a voltage? Shunt or series? Shunt. Then short. This was connected here to do what? To mix a voltage, right? How you mix voltage? Series or shunt? Series. Series. Voltage, mixing, series. Then leave it open. So the effect of R1 and R2 at the output is in series. However, the effect at the input is R1 and R2 are going to be in parallel. Then you have a new amplifier, a new open loop amplifier. There's no feedback here. Nothing is taken from the output back to the input. No. You only see R1 and R2 are in parallel with this. This is R1 and R2 are connected here, and you do the analysis. The gain you are going to find here is not A sub F, it's A. But it's not A without these. It's A with these circuits in place, okay? So that's why we're going to give it another name as A dash. If you remove this completely and you short this to the ground, this is called A. But now if you keep them with this configuration, this is a new feed-forward amplifier. So we're going to call it A. Once you find we're going to call it A prime. Once you find A prime, then you're going to find beta. How we find beta in this case? Well, beta was like this. This is R1, this is R2, and this is the input of beta, which is V out, and this is the feedback, which is VF. Okay, we can draw it this way. V out, VF, R2, R1. So I'm going to apply a voltage source here that's called V out. Now, for this one, to read the VF, should I short it or leave it open? Open, because you cannot short this to the ground, right? You need to leave it open. So leave this open. Now, what's beta? It's going to be beta V in this case, because it has input voltage and output voltage. So it's going to be V out, VF, divided by V out, at the condition that VF, let's call it, this current I2 or I1 or whatever. The condition is I2 is 0, okay? Meaning that you leave this open. So under this condition. So how much is this? What's the ratio of VF divided by V out? Voltage divider, right? So this is R1 divided by R1 plus R2. Can someone roughly tell me how to find the gain of this thing? the ideal value, okay? But this is not a feedback. I'm talking about A prime. I'm not talking about AF. So remember, now we have three amplifiers, okay? We have A prime, and we have A sub F. What are the differences between these three? A is this amplifier in this direction without this and this. If you short circuit this, remove this, this is your A. A prime is the same amplifier but with the effect of the feedback at the output and the input. So this is a new one. It's not the same as this one. And it's going to be less or higher. What do you think the relationship between these, or which one is higher, which one is larger? A, of course, because this one has a loading effect, right? So A prime is going to be slightly smaller or smaller than A. Then AF, which is, what's the relationship between A prime and AF? Now this is the one that we're going to use the formula. Okay? I'm not going to use this here. I have to use this because this one includes the effect of the feedback network, the loading effect of the feedback network on the amplifier. Okay? So, 1, you find beta. You did find it. 2, you find A prime. 3, you apply this formula and get the A feedback. Okay? For this one, you find just, if you can say, this one, these two are going to be in parallel with this, so this is going to reduce the gain. And also, this one, you can assume it is connected to the ground, right?
Because no current.
Because no current, and, you know, so this one, you can say this is a ground as well, right? Because, do you have any current here? Why?
It's a voltage controlled.
No?
It's a MOSFET.
It's a MOSFET, okay? The MOSFET, the current in the gate is 0. And if the current is 0, the drop here is 0. If the drop is 0, then this voltage is the same as this voltage. If this voltage is 0, then this voltage is also 0.
So we're not measuring, we're not accounting for the gate capacitance.
No. Here we just want to simplify things without talking about the capacitances here. Because if we add the capacitances as the previous chapter, these things are going to be very complicated. We just would like to analyze the circuit as assuming that all the high frequency capacitors are open and all the low frequency coupling and bypass capacitors are short circuit. Okay? The mid-band gain. We're talking about the mid-band frequency. Okay? So you understand now the difference between this, and this?
Yes.
This is what we're going to do. Okay? We have an open loop gain without the feedback. And then an open loop, a new one that's with the feedback effect but without the feedback connected. There's no feedback here. Then we have this with the feedback. Okay. One more thing. If you have RS here and you have an RL here, include them in calculating this one. Don't exclude them. Because what's V out? What's the gain? It's going to be V out over VS, not this voltage, not VGS. Or actually VG, okay? Because S is not ground. I assume here is not ground. So the output gain, so the gain A prime now is V out over VS. And this includes this and this. However, Rn feedback or Rn prime, okay, so Rn prime also is going to be here. And R out prime also is going to be here. So in calculating A prime, R input prime, R out prime, include the load resistance and the source resistance in the calculation. Now after you do that, you're going to get rid of them. If you'd like to find just the resistance from here, we're going to call it Rn. Okay? And this is going to be R out. But for now, just try to understand this, and we're going to get back to the resistance later on, okay? So, if it is shunt, shorted, if it is series, separate, or just keep it open. Any question about this? Is it clear? Okay. Then you draw the basic amplifier circuit A prime. This is A prime, right? So A prime has no feedback, but it does have the effect or the loading effect of the feedback network at the output and the input. Include RS and RL if there is any. If the circuit has RL and RS included in the calculation of A prime, meaning that if you have RL, what's the effect of RL in the circuit? When you calculate the amplifier, that will reduce the gain because RL and this series connection and RC, the three of them are going to be in parallel. Okay, so don't say, okay, I'm calculating the voltage gain up to this point without RL. No, include RL. Same thing for the RS. Don't say I'm calculating the gain from this point. No, calculate it from the overall gain, from the source, the internal value of the source. So include RS. What's the effect of RS? Again, it's going to reduce a little bit the gain if you have a voltage divider. But in this case, it's you're going to have a voltage divider here, right? Because this is in series with 1 over Gm, right? Because between this point and the ground, you have 1 over Gm. Okay, so this is going to reduce the gain because of the voltage divider between RS and 1 over Gm. Okay, so include that into the calculation. Use Thevenin equivalent. Yeah, sometimes you are given a current amplifier, but the input is a voltage. But you know that this is a current amplifier. Input current and output current. Then you have to use the source transformation. Okay? So if I'm telling you that this is a current amplifier, but I give you a voltage, then you have to replace this Vs and Rs with not equivalent. Okay? You know how to transform a voltage source to a current source and vice versa, right? So if you know that this has to be a current amplifier, and the input was given in a form of Vs and Rs, you can convert this into a current source with this direction, goes with the polarity, and a parallel resistance, not in a series resistance. Rs is the same, or R Norton is the same as R Thevenin, and how much is this current? Vs over Rs. And you call it Is. So if you know that this is supposed to be a current source, convert it from voltage source to current source. Or if it's given as a current source and you know that it's supposed to be a voltage, then convert it back from current source to a voltage source. Okay? So this is what this point means. Norton equivalent or Thevenin equivalent as you go from voltage to current and current to voltage. Then you replace each active device in A prime. The only active device is this one here. So you replace it with its T model. Okay. So remove this and replace it with the T model. Then do the analysis to find A prime. So this is going to be a feed-forward circuit, but with the effect of the input and output resistance of the feedback network. Also find Rn prime and R out prime. Okay? And again, in Rn and R out, you need to include these two. Then you find AF, R sub IF, R out F from this table. Because you know beta, you know the gain now, which is A prime. So you find A feedback using this, Rn using this, Rn with feedback, R out with feedback using this, and so on. Okay. And you have to make a test once you find this one to see if it is very close enough to 1 over beta. Okay? Let's say that this one gives you 5, while 1 over beta is 100. There's something wrong, right? Because the ideal value of this, if the design is good, should be very close to 1 over beta. Let's take an example. So this is a feedback amplifier, operational amplifier with feedback, and it's a non-inverting amplifier. Let's apply the direct method, the loop gain method, and the systematic approach. Again, for the direct method, it's much easier to assume that this beta does not load this amplifier, right? Meaning that R1 and R2 are very large compared to R2. So if you have R1 and R2 very large compared to RO, what does this mean? If these two resistors in series are much, much larger than R out, what's the implication of this? It means that you don't have to do voltage divider here, right? Between the RO and R1 in series with R2. Okay, you have to find V out. Is V out the same as this voltage?
Yes.
If RO is comparable to R1 plus R2, no, they are not the same. But if R1 and R2 in series, they are much, much larger than RO, then yes, then this voltage is the same as this one. Because the drop here is going to be very small, right? You have something like this. I have this V, R1 and R2, and I have RO here, right? And I have V1 here, okay? Now, what do you think for this configuration? What do you think of V1 and V out? It's a voltage divider, right? So V out is going to be V1 times R1 plus R2 divided by RO plus R1 plus R2. But if you assume that R1 and R2 in series are much larger than RO, then this is going to be approximately the same as V1. Okay, only if R1 plus R2 are much, much greater than RO. So this is the assumption. Not only this, but we also assume that this one does not load this one. So the beta network does not load the A network, and the A network also does not load beta. What does this mean? It means that Ri is much, much larger than R1. Because this voltage is not just a voltage divider, right? You have to include Ri in the formula, right? But if Ri is very large, you can assume it's open, then this voltage is just voltage divider of V out among R1 and R2. So see, this is what loads beta. And these two is what loads A. So beta loads A and A loads beta. You know, they are the circuit. So if you assume no loading, there's no loading effect, then you assume that RO is much smaller than R1 plus R2, and Ri is much larger than R1. So the A network is not loading the beta network, and the beta network is also not loading this one. If you do this, things are going to be very simple, and this method works fine. But in reality, this is not the case, right? Actually, this is not larger than this, and this is not always larger than this. So if you assume this assumption, then V out is the same as this voltage, and this voltage is just constant, A or mu or whatever times V differential or input. And the V differential is the difference between Vs and Vf. So this voltage here, Vi, is this voltage minus this voltage, right? This voltage is Vs, and this voltage is Vf. So mu times Vs minus mu times Vf. We know that Vf is a voltage divider from Vo if we assume Ri is very large. So we're going to multiply R1 by V out divided by R1 plus R2. Again, this is an approximation. This is an approximation, and this one is also an approximation. Then, we go back here, substitute VF here, and then rearrange the terms to bring V out on one side, and Vs on the other side, and solve for V out over Vs is going to give you this, which is the open loop gain divided by 1 plus beta times the open loop gain. So this is A divided by 1 plus beta times, which we expected to. But is this accurate? No. Because of the assumptions we have. Now let's find Rn. How to find Rn? Well, we apply a test source, Vx, and we measure the Ix, or find the formula for Ix, and then solve for Vx over Ix. This gives us our input feedback without cutting anything. Keep everything as is. So the direct method, you don't cut, you don't short, you don't open, you keep everything as is, and you solve the circuit as is. So we now need to find the relationship between Vx and Ix with respect to all the parameters in the circuit, the constants. Well, we said that Vx, this voltage, is this one plus this one. Agree? So this voltage, if you extend this ground here, is going to be this plus this, right? KVL, right? Vi plus Vf. But we know that Vf is V out times R1 divided by R1 plus R2, which is a voltage divider, assuming that Ri is much larger than R1. Still, the assumption of no loading is still exists. So this is Vx. Now we can see that Vx now is a function of Vi and V out. It's not a function of Ix. We need to get rid of this and this to make it a function of Ix. Well, we know that V out, if RO is very small compared to the series connection of these two, is going to be the same as this one. So V out is mu Vi. We take Vi common. All what we need is to find Vi in terms of Ix. If you look at this, Vi is the same as Ix times Ri. So Vi is Ix times Ri. We take this and substitute it here. Now we have an equation that links Vx and Ix. We solve for Vx over Ix. This gives you this. So our input after feedback is the same as our input without feedback times 1 plus beta times the gain. It's much larger, right? Because mu is very large, mu times beta is large compared to 1, so this is much larger than this one. Sorry, this one is much larger than this one. Same thing for V out, for R out. We connect a test source Vx, find the relationship between Vx and Ix, and divide them to get the R out with feedback, without moving anything, without cutting anything. Okay. Again, what's Vx? Vx is this voltage plus this one, right? Vx is V across RO plus this voltage, this dependent voltage source. If we assume that this current is not going to go here because this is a large path, large resistance, and all the current is going to go here, then Ix times RO plus this gives Vx. So Vx is Ix times RO plus mu times Vi. Now we need to keep this as a function between Vx and Ix. So we need to get rid of Vi. Again, what's Vi? Well, you have to apply, for the R out, you have to apply this source and you short circuit any existing source in the circuit. So we shorted Vs, right? Now Vi becomes the same as Vf with a negative sign, right? Vi and Vf are the same, but the polarity is opposite. So Vi is negative Vf. So we take Vi out and we substitute it with Vf. But we know that Vf approximately is a voltage divider of Vx. So VF is Vx times R1 over R1 plus R2. So this Vi becomes negative beta times Vx. We substitute this one here. We get this equation. It links Vx and Ix only. We solve for Vx and Ix. Vx on one side, Ix on one side, and we solve. We get the same result that we were expecting. Our output with feedback is the same as our output, this one, but smaller. With feedback, it reduces the output resistance. So it's R out divided by the amount of feedback as before. So again, this direct method is easy. However, if with only assumption that everything is ideal, you don't have the loading effect. So it doesn't work if you have loading effect. Now let's move to the second method. And again, this method will give you only the feedback gain. It cannot give you Rn and R out. So this is a shortcoming of this method. This is why we need the third one. So this method, it says, well, you have to cut the circuit somewhere. Okay? Where we can cut the circuit, we can cut it here, here, or here, right? Which is the best, which one is the best location? Should we cut it here, here, or here?
The first one.
The first one here. Why? Because the input impedance here is very high, okay? So we don't need to terminate with anything, okay? But if you need to terminate it, let's assume that we have to terminate. We have to terminate with Rn here, right? But let's assume that it's very high. So I have to just draw R1 and R2, and then V test is going to be connected this way. So to find the loop gain, you apply this voltage source here, this source, and then measure the received voltage at the other side, and divide VR by VT with the negative sign. This gives you the A times B. Okay? This one. So if you cut this one here, you're going to end up with these two in series. And then you apply the test source and measure this one. What's VR? VR is V out times R1 divided by R2. Okay? And what's V out? Again, here we can assume V out is the same as this, or we can do voltage divider, right? Between this and these two in series. But again, we're going to assume R1 and R2 are very much larger than RO. So V out is the same as mu VI. Okay, what's VI? VI is the voltage across RI. So it is the same as VT, but with a negative sign. So VI is negative VT. So you substitute it here, you get minus mu VT. You substitute this one here, you get this one minus R1 over R1 plus R2 times mu times VT. Then you have a relationship between VR and VT. All what you need is to divide VR by VT with a negative sign. So the loop gain is VR by VT times negative, which is going to end up with this times this, which is correct, right? This is the feed forward gain, and this is the feedback beta. So it is beta times A. Then you divide the gain, mu by 1 plus A times beta, gives you the feedback gain, which is exactly the same as what we did before. But with this method, we cannot find our input F nor our output F. Now let's move to the most important one, which is the systematic approach. In this case, we have to remove the feedback network and attach it twice. One at the input and one at the output. So this is the circuit. Okay, in this case we don't have RS. And this was the output. R2. This is R1. Sometimes they reverse them for no reason, but anyway. By the way, don't follow the formula blindly, okay? Because sometimes we put R1 here and R2 here. Some other times you might find R1 and R2 here. Okay, so follow the understanding, okay? So don't have a formula sheet that says R1 over R1 plus R2. Okay, and end up, this is correct here, right? But if this was given as R2 and this is as R1, this is wrong, right? This has to be R2 over R1 plus R2. So don't follow, like don't just write formulas and apply them as is, okay? Make sure that you go with the circuit itself. So this is 2, this is 1. Okay, and this is plus, this is minus, this is V out, this is VF, this is VS. Okay, so we have a feedback network which is R1 and R2 as a voltage divider. We're gonna remove it and we're gonna repeat it twice. One time at the input and one time, because we need to keep the effect of, if you remove it completely, then you don't have any effect of feedback, right? So we need to have a feed-forward amplifier without any feedback, but with the effect of feedback at the output and the input. Now, what should we do with this and what should we do with this? This is supposed to be here, which is mixing voltage in series. So leave it open. This was supposed to be here, which is sensing voltage in shunt, so then you have to short. Okay. Once you short R2 to the ground, then R1 and R2 becomes parallel. So it becomes like this. But this node is the same as this node. Okay, see, this node is ground, this node is ground, this node is ground. So we can put them like this. So this becomes R1 in parallel with R2. And this becomes R1 in series with R2. So this is our new amplifier. Does it have any feedback? No. Nothing is fed from the output back to the input. But does it have the effect of feedback? Yes. Okay? So this is not the amplifier A, the original amplifier A. This is called A prime. Okay? Question? Okay. Now, if you have an RS, it has to be here, right? If you have RL, it has to be here. Then the next step is to replace this with its model. What's the model of operational amplifier? You have Ri. You have RO. And you have the dependent voltage source that is, call it mu. We change it to mu not to confuse with the A, so let's call it mu. And times V input, whereas V input is this one. The V differential, sometimes we call it V differential. Is that the voltage between the two differential inputs. Now we have a simple circuit. We can find the gain. How to find the gain? Here there's no feedback, so the analysis is going to be much easier, right? With no feedback, the analysis is easy. We need to find Vs to V out, right? We can take it into two steps, Vs to Vn and Vn to V out. So what's the relationship? So V out over Vs is Vn over Vs times V out over Vn. What's Vn over Vs? This is a voltage divider, right? And if you have Rs here, you have to consider Rs in the voltage division, okay? But now, since we don't have, so we're going to keep it this way. So this is Ri divided by Ri plus R1 parallel to R2. Okay? So this is this one. What's V out over Vs? Vn. So V out over Vn is, what's V out? Is this voltage times this resistance divided by summation. So this is mu Vn times R1 plus R2 divided by R out plus R1 plus R2. All this is divided by Vn. Is that correct?
Mhm.
Then you cancel Vi. And with Vi, this is going to be mu. So let's write it here. Mu R1 plus R2 divided by R1 plus R2 plus R1. Which is this one? Mu Ri, R1 plus R2, Ri plus R1 parallel to R2 times Ro plus R1 plus R. Okay. Now, someone might claim that this is not the same as what we got here. Actually, this is more accurate. Okay, but actually, this is not. We haven't found the V feedback. This is V feed forward, right? This is the A prime, okay? This is without feedback. How to find A, VF? Well, we have to take A feedback, A feed forward, the new one, divided by 1 plus A times beta. Now the question, what's beta? I think we did it many times, so beta is the voltage divider. So it's R1 over R1 plus R2. Okay? So all what you need now is to take this, plug it in here, here, and you take this, plug it in here. So the equation is going to be very large, right? This is why I didn't include it here, but you have to take this, put it here, and again put it here, and then beta, which is this one. Again, how to find beta? You leave this open, you apply a voltage source, find this voltage divided by this. Is the feedback quantity divided by the output quantity. So while the current is 0, meaning that this is open, because it's a voltage mixing, right? So you leave it open. So now if you assume that this RO is much larger than these, is much smaller than these two, you can cancel RO, right?
Mhm.
Non-loading effect, right? And if you cancel this, this is going to cancel with this.
Mhm.
And if you assume that this one is much larger than these two, okay, so this is going to be Ri, right? If this Ri is much larger than the parallel combination of these two, then this term is going to be Ri, so it's going to cancel with this. So the whole term approximately is just mu. If you have this is very small, you can assume it's a short circuit. If this is very large, you can assume it's open circuit. And in this case, the gain is just mu. And then you divide this by 1 plus mu times beta, which is exactly the same as this one. So approximately, this is a more accurate one, but approximately this will approach 1 plus R2 over R1 if we assume that these two are much larger than this one, and this one is much larger than these two. Okay? Now the question, how if we have RL and RS? What's the modification? You have this, and we have RS, and we have RL. How is this going to affect the gain?
It's gonna decrease.
It's going to decrease because this will take some portion of the voltage drop, and this is going to reduce the parallel combination, is going to reduce the output resistance, so the voltage drop here is going to, the voltage divider is going to reduce. Okay? So you need to include this. And you need to include this in finding the Rn prime. If you decide to find Rn prime, you have to include this. And if you'd like to find R out prime, you have to include also the Rn. And at the end, you need to get rid of them. Okay? Any questions? No questions means it's easy to understand. It's too much.
Too much.
Too much.
Too much.
Okay.
What is the purpose of R out prime and Rn prime as opposed to Rn and R out?
So Rn is just this one. Rn prime is with this effect.
Well, and Rs, right?
Oh yeah, and Rs if it does exist, yeah.
So why do you include Rs? Because typically, the way that I think of the input resistance is, you know your source resistance and you're trying to figure out how much of that is actually making it into the amp.
Yeah, but if we assume that there is an Rs here, it's gonna affect the forward voltage amplifier for sure. So you have to include it in calculating the overall gain and Rn prime. Okay? Because you cannot apply this equation here, okay, without including Rs and RL here. It has to be included. Okay? Otherwise it's gonna be a different circuit, right? So you have to include, don't say, okay, this voltage source is out of the equation, okay, with its resistance. And we're gonna start here. You can do that if you are sure that Rs is very, very small, or ignore. You can do that. But if Rs is not very small, then you have to include it in the calculation of the A prime, Ri prime and R out prime. Okay? Try it and you will see the difference. It's not the same. Okay, now let's move to the R in and R out. What's R in here? Before the feedback, it was Ri, right? After the feedback, how much is the resistance you see from this side? Again, this source doesn't have Rs, right? So you're gonna see, if you're looking from this side, Ri prime is this in series with this, right? So Ri plus R1 parallel to R2. Well, we know from the table, from this table, that for a voltage amplifier, Rn increases by the amount of feedback. So we have to multiply Rn prime by the amount of feedback. But in this case, Rn prime is not Rn, and this is AV prime, not AV, and beta is the same, which is R1 over R1 plus R2. How about the R out? Well, we don't have a load here, so we just have to consider this and this. To find R out, you have to look to the circuit from this side, and you short circuit the source. If you short circuit this, VI becomes 0. If VI becomes 0, this voltage source becomes 0, meaning shorted. If this is shorted, then R out is going to be in parallel with R1 plus R2. So this is R out prime. Again, if you have RL, you have to add parallel to RL. And then take it off at the end. Then, from the table, we know that R out should be smaller because this is a voltage amplifier. So we have to divide it by the amount of feedback. The amount of feedback in this case is 1 plus AB prime times beta. Again, if you remember that condition, If R1 parallel to R2 are much smaller than Ri, and R1 plus R2 are much larger than R out, then this simplifies to this simplifies to this simplifies to this, which is exactly the same as the other methods, right? Okay, let's do this example. Without looking into this, okay, what do you think? Is this what we are mixing and what we are sensing? Let's start with mixing. First of all, where is the feedback network? It's only RF, right? RL is not part of the RF, of the feedback network. So this voltage is VF, right? And we are mixing it as series, right? Because if you see the feedback resistance, both terminals in the input circuit, that means you are mixing a voltage, right? You cannot, because this one here, if you extend this one like this, you have a loop here, right? So this loop includes this as a series component, right? So that means you are mixing a voltage. Now, since the current comes here, we are not sensing a voltage, okay? Because otherwise this is going to be V out and VF at the same time. So we are sensing a current. So this is the current, and we are mixing a voltage. So if you sense a current and mix a voltage, this is transconductance, because it's I over V. So it's a transconductor. This is example 11.7. So what we're going to do, first of all, we're going to take the feedback network out, which is this one. And it has input port and output port. Now the input port was current, right? So we're going to connect the current source. The output port was voltage. Mixing a voltage, right? So should we short it? No, we have to leave it open to be able to measure the voltage. So this is the feedback network. You have a current source that gets in, which is this one, and a voltage that gets out. So how much is beta in this case? First of all, if this A is a transconductance, then beta is the opposite, trans resistance. So the unit of beta is going to be ohm, right? So this is a very important test, okay? Beta, this is why we call it beta Z. It's an impedance, it's a resistance. It's VF over IO. What's the relationship between VF and IO? Ohm's law, right? This current has no way except to go through the RF, right? So IO times RF gives you VF. So VF over IO is RF. So the feedback network is just RF. And here it's not less than 1, right? It's not less than 1. It's a large quantity, it could be 1 kilo ohm, right? Then, once you know beta, you know the ideal value of this is going to be 1 over beta, which is 1 over RF. This is the ideal value of this one. Okay? And by the way, the importance of this transistor is to reduce the loading effect from the operational amplifier. So we added this to reduce the loading effect of this RL and RF from the output. Why? Because the current here now is, how much is this current? 0, right? So you are seeing infinity. Imagine if you connect this light right away here. So this is going to look like a loading. This is going to load this. But now when you put this transistor, no loading. So this is just to protect or to improve the output.
It looks like that's also another amplification stage.
Yes. Yeah.
So just common source.
Yeah. What configuration is this? The input is applied to the gate, and the output is taken from the drain, and this is common. So this is a common source. So could also provide amplification, but also the most important thing is that it has a very high input impedance. So this guy is not seeing these things at all. Okay. Okay. Now, what we should do next? We we should take this circuit and add it twice. One here and one here. Okay, for the one here, what should we do with this? Should we short it or should we leave it open? If you cut here and keep this at the output, this was supposed to be mixing voltage. So it is connected in series. Series, leave it open. Now if you give this one here, what you do with this terminal? This was connected to measure current. How we measure the current? Series. So leave it open. So you're gonna have something like this. RF and RF. Okay? This is the model for the operation amplifier. And this is the model for the transistor. So you replace RF twice, one time at the input, one time at the output, and leave this open, and then replace this with its model, and start analyzing the circuit. Okay, so RF is here at the input. So we broke the feedback, but we kept its effect at the input and output. This is the main idea. So we came up with a new amplifier that doesn't have feedback. But that amplifier is not this and this only. No, it has this and this. So it's not A anymore. It's called A prime. It's a new amplifier, but doesn't have a feedback. Now we need to find A prime. Now we have RS and we have RL. So we have to include them in calculating A prime, RN prime, and RL prime. What do you think is the gain? How to find the gain? From VN or VS all the way to the current. The output is a current, it's not a voltage. So we need to find I out divided by VN. How to do that? Well, we have to go stage. So we're gonna find the relationship between this and this, then this and this, then this and this. Okay. Let's write it here. So, of course, it's not this circuit. I'm going to erase it.
There's at least one component I think you could omit. I see at least one component you can omit from this.
Which
RO1 in the center block.
RO1, this one?
Yeah.
Yes. So this voltage is the same as this one. So RO1 has no effect. So the gain, and what's the substrate of this gain? It's a transconductance, right? So we should call it AG, transconductance. And prime is, what's the output quantity? It's a current, right? What's the input quantity? That's a voltage. Then we can divide it into stages. It's V, it's called I differential, okay, divided by VS times something over VI differential, which is going to be this voltage, VGS2. And final stage is times something over VGS2, which is I out. What's the gain from this point to this point? From this to this? Voltage divided. This is going to take portion of the three portions. So it's going to be RID divided by the three of them.
Will it be negative based on the polarity for that one?
That's correct, yes. If this was the polarity, based on the original circuit, the plus was here, okay? The plus is not here. Why do you think the plus is here? Why didn't we do it the other way around?
Because of the common source.
That's correct, because those provide a negative, right? And if this has negative gain, this positive gain, if this was positive, then the loop gain is going to be negative, which is wrong. If you have a negative A times beta, this is a negative, this is a positive feedback. So if this provides negative, this has also to provide a negative, so they cancel each other. Okay? That's correct. This is good. So this is negative R input differential divided by R input differential plus RS plus RF. We are done with the first part. How about VGS over VID? This over this. VGS2 is the same as this.
Yes.
So it's A1 times ID. So this is A1 times VID. Okay, and divide by VID is going to cancel, right?
Yes.
So the second stage is providing just a gain of A1. How about the third? Okay, let's do it here. IO divided by VGS2. This current is this current multiplied by this is current divider, right?
Yeah.
So this current with respect to this current is a current divider with a negative sign, right? You see the negative sign here? Because this goes this way and this one goes this way. So there is a negative sign of the current, which is GM2, VGS2,
VGS2 cancels.
exactly, times R2, RO2, if we consider it, divided by RO2 plus RL plus RF. Now you divide all this by VGS2, this cancels, and this is going to be negative. There's a negative here, right? It's going to be negative GM2 RO2 divided by RO2 plus RL plus RF. See again, and I don't think this is difficult now, right? We practice. This is what you missed in chapter 7, how to analyze a circuit like this. Okay? So we can combine A1 and GM2 as constants together. This voltage divider, this voltage divider. Now, to approximate this equation, well, you can assume that Ri input differential is much larger than these two. In this case, this is going to vanish, right? And if this is deleted, Ri differential could cancel, and this becomes 1. If RO2 is very large, which is the case, it's 200, 500, 300. So this is going to be much larger, then you remove this, then you cancel. So approximately this is A1 times GM2. Okay. Now how about Rn? If you look at the circuit from this side, what do you see? The 3 in series. So Rs plus R input differential plus R. Okay. How about if you look from here? You have to short circuit this. And if you short circuit this, this becomes shorted. If this becomes shorted, this becomes 0. If this becomes 0, this becomes open. 0 means open, right? Because this is a current source, this is a voltage. So open means that when you look from this side, you see this parallel with this, right? So it's RO. Oh yeah, sorry. What the mistake I did is I considered the output as a voltage, but it is not, right? We are not measuring the voltage across these two. If the measurement output measurement was a voltage, that would be correct. I had to take this in parallel to this. However, the output is current. So to see the resistance the current seeing, you have to cut the circuit and look inside after you cut. So we need to see the resistance seen by the current, not seen by the voltage. Okay? Is Similar to if you can connect the current source and you measure the voltage divided by the current at this here after you cut. So if you cut here and you assume this one open, and you cut here and look into the impedance from here, what do you see? The three are in series, right? So it's RO2 plus RL plus RS, okay? And this simplifies to just RO2. This simplifies just as R input differential, okay? We know from the table that to find the feedback gain, you have to take this gain divided by 1 plus A times beta. We know beta from the previous slide, which is F RF. We know A, so we're gonna attach it here twice. For the RIF, it's this RI prime times, because it increases, because this is a voltage side, right? So it increases the resistance seen by the voltage, and this is a current sensing thing. So so it is increased as well, right? So on this side, because it's in series, right? So it's RO prime times 1 plus AB times B. Any questions?
So, say for example, we had like something similar to this one, right?
This one?
Yeah, where we like had VO on the resistors for the previous, then we would actually have to make it parallel.
Can you say that again? So if you have
Oh, yeah, so like, for example, you know how this one that says VO on next to
This one?
Next to RL, right?
Yeah.
If, for example, like, we would
Yeah, if the output quantity is a voltage, then you need to look into the circuit from a voltage point of view. So the voltage takes things in parallel, right? But if it's the current, then you have to cut and see how the current sees the resistance in the loop. Okay. So this one is the trans resistance, with this being the feedback. And if you take it out, it's going to be like this. And since the output is voltage, the feedback is current, then you short circuit this, right? Because this was current. And then you can find the relationship between VIF over V out. And if this is the case, this is going to be minus 1 over it, because the current is going this way while the voltage is measured this way. So there is a negative sign. Now we isolated RF, then we have to add it twice. Tell me how to add it twice. First of all, this is what? Is voltage mixing or current mixing? Current. And this is voltage. So this is shunt and this is shunt, because you mix current as shunt and you sense voltage as shunt. So if you take this out and put it twice, so one is going to be here and one is going to be here, right? What do you do with these two terminals? This was supposed to be here, so it has to be shunt. And this was supposed to be here, it has to be shunt. So the circuit is going to look like this. Okay? So you have to repeat this twice, one in parallel with RL and one in parallel with RS, and then you remove this and you replace this with its equivalent circuit. So you get this thing. Analysis here is very simple, right? If I ask you how much is this voltage divided by this current, how do you find it? First, you have to go from this current to this voltage, and then from this voltage to this voltage, right?
Yeah.
What's the relationship between this current and this voltage? You take the 3 resistors in parallel, multiply them by this current with no negative sign, because the current is going with the same direction. So multiply this current times the 3 resistors in parallel, gives you this voltage, right? Which is this, right? And then you take this multiplied by mu, gives you this voltage. How are we going to find this voltage? What's the relationship between this and this?
R naught plus RL parallel with R.
Exactly, RF and RL in parallel. And these two are in parallel, and you do voltage divider with RO. Okay, so these two are in parallel first, because the voltage, the V out is across these two. And then you take voltage divider. And you apply this, you're going to give you this. Okay? where Ri prime is the three together, right? So if you look from this side, how much is the resistance you see? What's Rn to prime here? This parallel to this, parallel to this. If you look from this side, this is going to be shorting, right? So this parallel to this, parallel to this. So R out prime is the three output resistance in parallel. R in prime is the three input resistance in parallel. You take this divided by, according to the table. You gotta have to go to the table and see what improvement, okay? You don't need to memorize it, but it's good to understand it, okay? So this is a voltage, so you need to see a higher resistance, right? Sorry, this is a current, so it should be smaller resistance. And this is a voltage, so you should see smaller resistance, because this is R out, right? So R out should be smaller, and R in should be also smaller. Okay? This is the final one. I leave it as an exercise. If you have any questions, just let me know. It's the same thing, so you have to take these two. This is a current, this is a voltage. So when you cut here, are you going to short it? What do you think if you cut here and attach it here? This is what? This is current, right? Current is mixed in shunt, so you have to short. If you cut here, this is current, and current is sensed in series, so leave this off. Okay, so you're going to have R1 and R2 in series here and in parallel here. And this is beta, how to find beta, and this is the new circuit with everything, and you need to find the gain from this point to this current, and so on. Okay? Usually the current amplifier is the most difficult one, so don't expect to have something current, just study the other three ones, okay? Any questions? And this is the final table that summarizes everything. Okay, so this Friday we're going to have like a problem solving session at 2:30 p.m. Use the link that I provided in the main page for that office hour. And by the way, I don't see anyone utilizing the office hours, okay? So my office hour is going to be Tuesday and Thursday, I would say from 12 to 2 p.m. anytime. If that doesn't work, just send me an email and I can meet with you individually, like over Zoom or personally in the office. If these two times not work. Okay?